Have you ever just, looked at a landscape and wondered what's really going on underneath your feet? Every single mountain, every valley, they were all shaped by these incredible forces over millions and millions of years. Well, geologists actually have a way to read that story. It's called a geological map, and it's basically a blueprint for the Earth itself. So let's start cracking the code. Okay, so at first glance, I know what you're thinking. This looks like a total mess, right? It's just a jumble of colors, lines, and some really weird symbols. This is a real geological map of a place called the Squiggly Prairie. And yeah, it might seem chaotic, but trust me, it is packed with clues about a super dramatic history of bending, breaking, and shifting rock. So that's our mission today. We are going to become geological detectives. We're going to figure out how to decode all the clues on this map, the folds, the faults, the layers, and uncover the epic story of what exactly shaped this landscape. All right, our first set of clues are these big, sweeping curves you see in the colored bands. Now, these represent places where immense geological pressure has literally bent solid rock. We call these folds. Okay, think about it like this. Imagine you've got a big rug on the floor. If you push the two ends towards each other, what happens? Of course, it buckles up and creates a whole series of waves. While the Earth's crust does the exact same thing when it gets squeezed by tectonic forces. Over millions of years, layers of rock that were once totally flat get slowly compressed and bent into these massive structures. This slide right here is where it gets really cool, because this shows how we connect that 2D map to the 3D reality. So the simple stripes of color we see on the surface, like on the left, are actually just the very tops of these huge U-shaped folds hiding right underneath, as you can see on the right. And this downward arching fold, it has a specific name. It's called a syncline. The easy way to think of it is like a sink or a trough or a basin. Now, the absolutely crucial part here, the way you identify it, is that the youngest rock layers are always found right in the center, or the core, of the fold. As you move away from that center, the rocks get older and older. And of course, if you have a downward fold, you've got to have an upward one, right? This is an anticline, and it arches up, kind of like a hill. It's the total opposite of a syncline. In this case, the oldest rocks are pushed up into the core, and the layers get younger as you move outwards. So just remember, syncline for down, like sinking, and anticline for up. All right, time for our next clue. If we go back to our map, you'll notice this sharp, straight line that just cuts right across our beautiful folded rock layers. This is what happens when the pressure just gets to be too much for the rock to bend anymore. Instead, it breaks, and that break is called a fault. So there are really two main forces that cause faulting. Over on the left, you've got tension. That's when the crust is being pulled apart or extended. That creates something called a normal fault. Then on the right, you have compression, where the crust is being squeezed and shortened. And that results in a reverse fault. So pulling apart versus pushing together. Now, to figure out which way the rocks have actually moved, we just need two simple terms. Imagine you're a miner, and you're standing in a tunnel that runs right along the fault line. The block of rock that's hanging over your head, that's the hanging wall. And the rock that's down beneath your feet, that's the footwall. Super simple. Hanging wall above, footwall below. So in a normal fault, which is caused by that tension pulling the crust apart, gravity just kind of does its thing. The hanging wall, that's the block above the fault, it just slides down relative to the footwall. And this whole process stretches and thins out the Earth's crust. But in a thrust fault, which is a type of reverse fault caused by compression, the exact opposite happens. That intense squeezing force actually pushes the hanging wall up and over the footwall. This process shortens and thickens the crust. And as we're about to see, this is powerful enough to build entire mountain ranges. All right, detective, we now have our key tools. We know about folds, and we know about faults. So it's time to head back to our Squiggly Prairie map and finally piece together the full story. Let's solve this puzzle. So what's the first thing a geologist does? They find the center of the action. They trace what's called the fold axis for each of those big bends in the rock layers. This is basically just an imaginary line that runs right down the middle of every single fold. Next up, they figure out the relative age of the rock layers. Let's just go ahead and number them 1 through 7 from oldest to youngest. And by looking at that pattern, is the youngest in the middle or is the oldest in the middle, we can now clearly see which folds are our downward arching synclines and which are the upward arching anticlines. The pattern becomes clear. Now for that fault line. Look closely at the rock layers on either side of that solid black line. On the left side, we see older rock layers exposed at the surface, but on the right side, we see younger layers. So, think about it. How can old rock end up right next to young rock? The only way that can happen is if the older rock was pushed up from deep below, so that tells us the left side of the fault must have moved up. And because we know the left side moved up, we can identify it as the hanging wall being pushed over the footwall. This tells us everything. It means the fault was caused by compression. And boom, just like that, we've read the blueprint. We now know this entire landscape was formed by these immense squeezing forces that first folded the rocks, and then, when they couldn't bend anymore, broke them, thrusting one whole side up over the other. But hold on. Here's the absolute best part. Reading the map isn't just about understanding the past. It lets us do something truly incredible. It lets us see the hidden world that's right beneath the surface, a world that no one has ever actually laid eyes on. And this is the grand finale. By taking all the information from that flat 2D map, the angles of the layers, the types of folds, the direction of the fault, we can actually draw a cross-section. We can visualize the entire underground structure. What started as just a flat map becomes this dynamic, three-dimensional picture of the Earth's crust. It's amazing. It's so important to remember the incredible scale of what we're looking at here. These are not small events. These are forces that operate over millions of years with just unimaginable power. The crust breaks and it buckles, entire mountains rise up, and the world we know is literally created, piece by piece. And look, this isn't just some abstract diagram in a textbook. Check this out. This is the McConnell Thrust, a massive fault in the Canadian Rockies. This single compression event pushed ancient rock layers up and over younger ones for dozens of kilometers, and in the process created the magnificent Front Range of the Rocky Mountains. The exact same principles we saw in our little map created this. So that's the real power of a geological map. It's so much more than just a bunch of lines on paper. It's a key that unlocks the epic, violent, and beautiful history of our planet, a story that's written directly into the stone itself. So, the next time you're out and you see layers of rock that are tilted at some strange angle, you'll know you're looking at just one piece of a much, much larger story. It really makes you wonder, doesn't it? What story is the ground beneath your own feet just waiting to tell?